let's just go through the remaining question from June 2021 P21 first. All right. Okay, so if you look at question 5 from June 2021 P21, state Kirchhoff's second law. Kirchhoff's second law is just you saying the sum of EMF is equals to sum of PD around a closed circuit loop. Okay, this one is worth 2 marks. So some keywords that you always need to ensure is always written down is you saying sum of EMF and sum of PD. And not to mention, you need to mention that it's a closed circuit. Okay, these are the keywords that ought to be inside your question. Now, if this one is written in a mathematical form, in an equation form, this one just means this sum of EMF equals to sum of PD in a closed loop. Okay, this one is one way of looking at it. Now, if you then look at part B, a battery has an EMF of 4 volts and internal resistance of 0.35 ohms. The battery is connected to a uniform resistance wire XY and a fixed resistor of resistance R, as shown in the diagram below. From here, they mentioned that wire XY has a resistance of 0.9 ohm. The potential difference across wire XY is 1.8 volts. Calculate the current in wire XY. This wire XY that they're talking about is actually this wire here. It has a particular resistance to it, where the resistance is 0.9 ohm, and the PD across it is 1.8 volts. Okay, so they want you to find out the current in the wire XY. This one you can just straight away apply V equals to IR for the wire itself. If you apply V equals to IR for the wire itself, the PD across it is 1.8 volts, the resistance is 0.9, so eventually you're going to get the current value of 2 amps. Okay, so one thing I should probably mention again also is that when you use a calculator to calculate out the value, you will get a nice value of 2 amps. But this one, if you write it as your answer, is considered as 1 SF. So please don't write your answer as 1 SF. Usually final answer must be minimum 2 SF, maximum 3 SF. So that's the reason why I wrote it as 2.0 here. Okay. The only exception where you will ever write your final answer as 1 SF only is when you're talking about absolute uncertainty. Okay, this is about the only time you will ever write your answer in 1 SF for absolute uncertainty. Okay, now if you move on to part 2 is asking you the number of free electrons that pass a point in the battery in a time of 45 seconds. Okay, so in your case, whatever current that was actually flowing through your uniform resistance wire will also be the same current flowing through elsewhere in the circuit because it's a series connection. So the current flowing through your battery itself is actually the current that you calculated initially. So you want to find the number of free electrons. You will make use of the definition of current that you would have learned before this, where you say that current is rate of flow of charge, is total charge divided by time. So this one, you can further expand it to become N times Q divided by T. So where N is your number of free electrons, and then Q is your charge of electron. Okay, the big Q you see here is actually just referring to total charge. Okay, so if you sum everything in, you should get the answer eventually. So this is 2 equals to N times 1.6 times 10 power minus 19 divided by 45. The 45 here is your second. Your answer will give you 5.63 times 10 power 20. Okay, so this is number of free electrons in that particular time of 45 seconds. So this is pretty straightforward. Now then, after that, if you move to the bottom part where they ask you to find out the resistance R of your wire, the resistance R of your wire is this one. Okay, so just now the uniform resistance wire that they mentioned to you was this one. You already found out that the PD was 1.8 volts and the resistance here is 0.9 ohms. So here what you're interested to find out is what is the value of the resistance R. Okay, now before that, you've also found out the current moving through your circuit. The current flowing through your circuit, you've already found it out as 2.0 amps. So if it's 2.0 amps through your uniform resistance wire, it will also be 2.0 amps through resistance R here. Okay. So to find out the value of R, you can actually make use of Kirchhoff's second law here first, where they say sound EMF is equal to sound PD. You apply Kirchhoff's second law for this loop here. There's only one source of EMF, which is E. Let's call this 4 volts as your E. And then you have 3 different sources of PD. You have the PD for your uniform resistance wire. You have your PD through your fixed resistance R. You also have your PD through your internal resistance. So here, if I write it out, it'll be voltage across the wire plus voltage across the resistance R plus voltage across the internal resistance. But since the same current is flowing through them, I can actually further express my equation as E is equals to I times R of the wire plus R plus small r. Okay. The same current flows through them, so I know I can actually factorize them out. All right. So here, just sub in your values. EMF is 4. Current is 2 ohms. Resistance of your uniform resistance wire is 0.9. The big R is what you want to find out. The internal resistance is 0.35, which you already know. So solve for that one, you will eventually get the answer as 0.75 ohms, just like that. Okay, just apply Kirchhoff's second law and you should be able to find the answer. All right, the ones that is just written in red here is actually the same variation of what I just did. Okay, so it's actually still based on Kirchhoff's second law. So this one I won't really talk so much about that. If you look at part C, you have a cell of EMF 1.2 volts that is connected to a circuit in B as shown in figure 5.2. The cell of EMF 1.2 volts is this. The circuit in B is actually this. Now, if you look at the diagram, you should be able to identify that this is actually a potentiometer. Okay, and then from there, they mentioned that the connection P, which is this point here, is moved along the wire XY, which is our uniform resistance wire from before. Okay, and then they continue moving it until the galvanometer reading is 0. So at this point here, your distance XP is 0.3 meter. Now, if you recall what you learned from a potentiometer, the moment your galvanometer reading reaches 0, you are interested in a particular length called the balance length. The balance length here is actually this wire XP here right now, or rather the length XP here. Okay, so once you reach balance length, there's another important thing that we know, that one being that the PD across the balance length, or the PD at the top, will be equals to the PD at the bottom, or in this case, it's actually our EMF. All right, so here we can actually say that the PD across XP is going to be equal to the EMF being tested here. So right now, if we know that the EMF that we're testing is actually 1.2 volts here, the PD at the top by right would also be 1.2 volts. Okay, this one will be for a length of 0.3 meter. Okay, now in part 1, the question wanted you to find the total length L of the wire XY. They want you to find the full length of the uniform resistance wire. Now, if you recall what you learned in the previous part of the question, in the previous page, they already mentioned to you that the full length of wire XY has a PD of 1.8 volts. So in our case, we can actually say that from here all the way to here, there's actually a PD of 1.8 volts. And we're interested to find out the length that corresponds to this PD. That length would be the full length of our wire right now. So when it comes to a potentiometer, there's always a relation that we would use, which is PD being proportional to L, directly proportional to L, so that V2 to V1 is equals to L2 to L1. So in our case, let's just consider the V2 and L2 being the full length case, and the V1, L1 being the balanced length case. We will get our ratios as 1.8 volts to 1.2 volts equals to L2, which is our full length, divided by the balanced length of 0.3. So eventually our final answer would be giving us 0.45 meter. This is the full length of our uniform resistance wire. So in our case, this is now 0.45 meter. Just let me rewrite this properly. Okay, so it's 0.45 meter here. All right. If you then move on to part 2, they mentioned that the fixed resistor is replaced by a different fixed resistor of resistance greater than R. So the fixed resistor that they are referring to here is actually this one. Okay. So from there, they then mention, state and explain the change, if any, that must be made to position P on wire XY so that the galvanometer reading is 0. All right. So what should happen to position P here? To get an idea of what is actually happening when the fixed resistance is increased, it will be better to just draw a diagram out first. So we have our cell connected to our internal resistance here, which is in turn connected to our uniform resistance wire over here. And then this uniform resistance wire is in turn connected to our fixed resistor right over here. And then that in turn connects back to our battery right over here. Okay. And that circuit is still connected to the EMF that is being tested. So we have this with the galvanometer connected to the wire. And the point where it connects to the wire is point P here. All right. So some things to note here would be the PD values across the wire in the first place. Just now, when you look at the early part of the question, it was already mentioned to you that the PD across the full length of the wire is actually 1.8 volts. Okay. So at that point, you had your resistance R here, you have your internal resistance small r here, and you have your EMF E here. Okay. So in our case, let's just also say that the PD across the fixed resistor is actually VR. The PD across the internal resistance is V small r, and the PD across the uniform resistance wire itself is V wire. Okay. Now, in our case, when the fixed resistance is increased, we are interested to find out what happens to the PD across the uniform resistance wire. There are two ways in which we can find this out. Now, the first way is by looking at the current that comes out of the cell. The current that comes out of the cell will be flowing like this. Okay. It will only be flowing within this top loop right over here. Okay. Now, if you recall what we learned in potentiometer before this, it was mentioned before that at balance length, in other words, when your galvanometer reading is already 0, current only flows in their respective loop, in their respective circuit. Okay. In a potentiometer, generally you have a top circuit as well as a bottom circuit. Okay. So current in the top circuit will only flow in the top circuit. Current in the bottom circuit will only flow in the bottom circuit when you reach balance length. So in your current case here, you already say that your galvanometer is supposed to reach 0. So you should have achieved balance length. Whatever current that flows in the top circuit will only remain within the top circuit itself, like what I've just indicated in your diagram here. And then of interest to you is this. When my fixed resistance has increased, no doubt the total resistance has increased too, which in turn causes my current flowing through the circuit to drop. But the thing is that if you look at the PDs inside the circuit right now, namely the PD across the wire, the PD across your fixed resistance, and the PD across your internal resistance, although the current has changed, the same current is actually still flowing through all three PDs. So from here, if I apply V is equals to IR for all three PDs here, I can still say that current through all of them is constant. So therefore, PD is proportional to R. Now for the fixed resistor, since I know that its resistance has increased, therefore, the PD across the fixed resistance would have increased too. And then from here, I can actually make one conclusion. If you look at Kirchhoff's second law, where sum of EMF is equals to sum of PD, I could say that the EMF is equals to the PD across the wire plus the PD across the fixed resistance plus the PD across the internal resistance. Now, the EMF value itself remains fixed. The PD across the fixed resistance will already determine that it's increasing. So therefore, the PD across the wire itself, as well as the PD across the internal resistance, should be dropping here. Okay, so the conclusion here that we get is that PD across the wire decreases. All right. Now, there's a second method that we can use to determine what happens to the PD of the uniform resistance wire. Now, if you talk about the total resistance inside the circuit right now, it is actually made out of the resistance of the wire added with the fixed resistance, added with the internal resistance. You can just add them all up because they're connected in series. All right. And then when it comes to the resistance of the wire, we know it is fixed. It did not change. The internal resistance is also fixed. It did not change. So the only thing that has changed here is the fixed resistance, which we said has increased. So looking at it here, we know that our total resistance would have increased too. And then from there, since R total increases, current will decrease. The current flow through our circuit, this current I here, would be decreasing. All right. And then from there, if you just specifically apply B equals to IR for the uniform resistance wire, let me just write it here. For the uniform resistance wire, if you apply V is equals to IR to the uniform resistance wire itself, there's one thing you can say about the resistance of the wire itself. The resistance of the wire would actually be fixed or constant here. Your question mentioned that they only increase the fixed resistance. All other resistances remain the same here. Okay, so in our case, if the resistance of the uniform resistance wire is constant, that will mean that the PD across it is proportional to the current through it. All right. And if you recall what we did above, we said that the total resistance here in the circuit has increased, so the total current here would have dropped. So the current through our uniform resistance wire itself would have also dropped. So in our case, we can now say this. I is dropping through the uniform resistance wire. Therefore, the PD across the uniform resistance wire would also be dropping. So we're getting the same conclusion as the first method here, where we said that the PD across the uniform resistance wire is decreasing. Okay, you can view this in two ways. All right. Okay, so how does knowing the PD across the uniform wire having decreased help us to answer this question right now? Now, if you recall what you learned from potentiometer, when your galvanometer reading is 0, you will get something called balance length. And from there, it was also mentioned that the PD across your balance length would be equal to the PD or EMF or whatever you're trying to measure. In other words, the PD at the top of your circuit will be the same as the PD at the bottom of your circuit. All right. So here, the EMF that you're trying to measure is actually 1.2 volts, okay? So if your galvanometer reading were to be 0 under both cases, the PD across your balance length, the PD at the top, will always be 1.2 volts, okay? Now, you consider this. From the previous part of the question, we already know that the uniform resistance wire has a total PD of 1.8 volts, and the full length of the wire was 0.45 meter. Now from here, we can actually work something out. If we know that 1.8 volts is for 0.45 meter, the PD per unit length, in our case, would be 1.8 divided by 0.45, giving us 4 volts per meter. So 1 meter of the wire here gives us 4 volts. All right. Now, this is for the case before you change the fixed resistance. Now, what happens when you change the fixed resistance? What happens when you increase it? Before this, we already established that the moment you increase your fixed resistance, the PD across your uniform resistance wire would actually drop. So if before this, it was at 1.8 volts, what will now happen is that it will actually drop to a value less than 1.8 volts. Say, for example, maybe it is now at 1.5 volts for our discussion here. So here, if we have 1.5 volts for the same full length of the wire, our PD per unit length would actually be 1.5 divided by 0.45, giving us 3.3 volts per meter. So in our case, you will notice that the PD per unit length has actually decreased. Before this, it was 4 volts per meter. Now it's 3.3 volts per meter. So the thing now is that for potentiometer, when your galvanometer reading is 0, your balance length, the PD across it, must be equal to whatever PD or EMF you're trying to measure. So in our case, we already know that we are trying to measure an EMF of 1.2 volts. For our case now, when we change the fixed resistance to a larger value, the new balance length must have a PD of 1.2 volts too. Okay, so based on the concept of PD per unit length, because our PD per unit length now has actually decreased, you actually would need more length to get back the same PD. In our case, the same PD here is actually the 1.2 volts. So here, if I will find out what is the new length required, let's just say here, the new length, the new balance length required, I take 1.2 divided by 3.3, I will get 0.36 meter. Okay, now look at what is the balance length before you change the fixed resistance. The balance length before you change the fixed resistance was actually 0.3 meter. Now, once you increase your fixed resistance, your new balance length is actually 0.36 meter. So from 0.3 meter to 0.36 meter, your balance length has increased. So your point P here needs to be moved towards the right. It needs to be moved towards the right-hand side so that your balance length is actually longer. Okay, in your marking scheme, they just say move it towards point Y, which is the same as you saying moving towards the right. Okay, so you look at the answer for this question, you would be written like this. You would say that the PD across the new fixed resistor is larger, thus the PD across wire XY decreases. This is based on the explanation here. Okay, now in order for your galvanometer reading to remain at 0, P must be moved towards Y in the first place. It must be moved towards the right. Because from what I explained, since PD is proportional to length and the PD per unit length has decreased, you need a larger length in order to produce back the same 1.2 volts. Okay, so this is for this question, right? The answer seems pretty simple, but the understanding requires you to know a few things. All right, that's what makes this question a bit hard, especially for potentiometer. All right, so let's move on to the next question. Now, for question 6, they mentioned this to you. You have a proton in a nucleus that decays to form a neutron and a beta plus particle. State the name of the other lepton that is produced inside your decay. So in your case, you know that you're talking about beta plus particle being produced here. Beta plus is actually your positron. It starts with a P, so you know it is proton, change to a neutron, giving you your beta plus particle, and your electron neutrino. So just fill in your proton number and neutron number, you will get this 1 here. All right. Then from here, this one we know is your positron. This one is your electron neutrino. This one is your neutron. This one is your proton. Okay. So these two are your leptons. Okay. So what's the name of the other lepton that's produced inside of decay? Is actually your electron neutrino, which is this one. Okay. Now state the name of the interaction or force that gives rise to the decay. The thing here is that usually when your proton decays to become a neutron, there's a change in the quark composition. Your proton is up, up, down. Your neutron is up, down, down. Okay, during the beta plus decay process, what happened here is that the up quark changed to a down quark. Okay, so the process that's responsible for your quarks changing flavor is what you call your weak interaction, or sometimes called weak nuclear force. Okay, the terms are interchangeable. So in your case, what's the interaction responsible? Either you say weak interaction or weak nuclear force. Okay, so that's for that. And then if you look at part 3, state which of the 3 particles, the proton, neutron, or beta plus particle, that would have the largest ratio of which will have the largest ratio of charge to mass. Okay, so which one has the largest ratio of charge to mass? So ratio of charge to mass is actually referring to this Q over M. Okay, so let's just call this ratio only. Okay, ratio of charge to mass is just Q over M here. Okay, they want the largest ratio. The ratio will be large if Q is large and M is small. This is number 1. Okay, so what do we know about proton and neutron in the first place? So if you talk about proton and then neutron and then your beta plus particle, if you're looking at their masses alone, say the masses, proton will just be probably 1U, neutron also 1U, but beta plus particle being an electron, an anti-electron, will be 1 over 2000 U. Okay, this is something that you need to kind of remember. All right. Okay, so this one is proton, neutron, and beta plus particle. Now, how about the charges then? If you're talking about the charge, for proton and neutron, proton, it has a charge of plus E, neutron has 0 charge, beta plus particle is also plus E. Okay, so in your case, neutron, you cannot consider the ratio of the charge to mass, because you see, if you sub Q as 0, your ratio is 0. There's nothing to do from there. because here the question wants the largest ratio of charge to mass. If you have 0 for your charge, there's no ratio whatsoever. Okay, so the only ones that you can consider is the first and third column, proton and your beta plus particle. Okay, but you will notice one thing here. You see, both proton and beta plus particle have exactly the same charge. Okay, so if you want to compare based on charge alone, they're both the same. There's nothing there you can do. But in terms of the masses, there's something you can say about them. You can actually kind of say something like this. You see, ratio is being Q over M. If the Q is the same for both cases, that means the ratio is actually just inversely proportional to M. So a small m will give you a large ratio. So you can clearly see that this mass here for beta plus particle is clearly so much smaller than your proton. So therefore, ratio of Q to M of beta plus particle is the largest. Okay, because the mass is the smallest here, so the ratio ought to be the largest. Okay, so the answer here is just beta plus particle. And then the next one is use the quark model to show that the charge on the proton is plus E, where E is the elementary charge. So this one is pretty straightforward. Proton is just consisting of up, down quarks. And you know that an up quark, the charge of an up quark is plus 2 over 3e. And the charge of a down quark is negative 1 over 3e. So if you have 2 up quarks and 1 down quark is plus 2 over 3e plus 2 over 3e minus 1 over 3e, giving you plus e. So this one is already shown for you here. Okay. All right. Then from there, if you look at part 4, now the quark composition of the proton is changed during the decay. Describe the change to the quark composition. So this one I already mentioned to you. Up, down, change to up, down, down. And up quark changes to a down quark. Okay. Or you can also likewise just say that up, down changes to up, down, down. Okay. Just like that. So that's for part number 5. Okay, part B that you see below, the one that talks about the nucleus X and nucleus Y being accelerated by the same uniform electric field, then determine the ratio of the electric force acting on nucleus X and Y. Electric field is no longer inside your syllabus in AS. It's actually being moved to your A2. So this one is no longer relevant for your AS exam, more for A2. So we are not going to discuss this. The same can also be said for the second part, where they ask you to find out the acceleration of the nucleus Y to the acceleration of the nucleus X to Y due to the field, due to the electric field. Again, this is no longer in your syllabus because it's in A2 now. So this one is out. Number 3 is also same because it's still talking about electric field. Okay. So part B we won't discuss because it's under electric field.